Preliminary investigations. Introduction. Students generally miss this step, but it should be clear that it is a very important step and gives an idea about the functional group of the compound, and even more than this, some preliminary tests specify a single compound, which however in no case should be considered as final. The important preliminary tests may be discussed under the following headings: physical state and color, solid and liquid, odor, ignition, ignition on china porcelain, action of 20% sodium hydroxide solution, action of hot concentrated sulfuric acid, reaction with ferric chloride, action of potassium permanganate. 1. Physical state and color. In organic compounds, the color is generally associated with the presence of certain functional groups, i.e., particular group in the compound is responsible for a particular shade. However, it should also be noted that several organic compounds are colorless in the pure state but oxidized to colored compounds by atmospheric air, e.g. amines. The different important groups along with their most usual colors are summarized below in the solid and liquid states. Solids. Color. Possible compounds: yellow, iodoform, benzoin, benzyl, anthracene, quinones, and nitro compounds. Orange, orthonitroaniline, pink, nathols, brown, diamines, aromatic higher amines, and aminophenols. Liquids. Color. Possible compounds: colorless to red-brown, amines, yellow to orange, nitro compounds. 2. Odor. Most of the organic compounds possess characteristic odor. The odor of some compounds is so characteristic that it can be used even to distinguish the particular class compounds or sometimes even a single compound from that of others. Color. Possible compounds: carbolic or phenolic, phenols, naphthalene-like, naphthalene, p-dichloro or p-dibromobenzene, mice-like, acetamide, bitter almond-like, benzaldehyde, nitrobenzene, pleasant, alcohols, ethers, esters, very pungent, low aliphatic acid and their halogenoderivatives. 3. Ignition. The nature of organic compounds, whether aliphatic or aromatic, can be established by the ignition test. The compound in question is placed on a nickel spatula or metallic coin. The latter is then heated first slowly and then strongly in a burner flame. If the compound burns with a non-smoky flame, it is an aliphatic compound. Expect chloroform, chloral hydrate and ethyl acetate, which burn with a smoky flame, while if it burns with a sooty or smoky flame, the compound is aromatic in nature. On complete ignition, if some residue is left, it indicates the presence of a metal in the compound. For establishing the nature of metal, the residue is dissolved in dilute hydrochloric acid and tested for metals like sodium, potassium, calcium, with the help of flame test or simple inorganic qualitative analysis. The aliphatic and aromatic nature of the compound may further be ascertained by the following tests. Nitration test. Take 1 gm, or 1 ml, of the compound in a test tube. Add 2 ml of concentrated nitric acid and 2 ml of concentrated sulfuric acid. Heat the contents for about 5 minutes, cool and pour the contents in cold water. Formation of a yellow, oily liquid or solid indicates the presence of an aromatic compound, otherwise it is an aliphatic compound. Le Rosen test. Take 0.2 gm, or 3 to 4 drops, of the organic compound, 3 to 4 drops of formaldehyde solution and 5 ml of concentrated sulfuric acid. Shake the contents well and then warm. Formation of red, orange, violet or green color or precipitate indicates the presence of an aromatic compound, otherwise it is an aliphatic compound. 4. Ignition on china porcelain. Place a small amount of the compound on a porcelain and then heat it first gently and then strongly. Note the change in appearance, the odor produced and the residue left. Following are the notable observations and inferences of various important compounds. Observation. Inference. Burns with luminous, aromatic or unsaturated, smoky flame, aliphatic compounds, smell of ammonia, amides, violet vapors, iodoform, chars but does not melt, uric acid, sulfonic acid, starch, darkens, swells, chars with burnt sugar odor, carbohydrates, tartarates, lactates, and some citrates. 5. Action of 20% sodium hydroxide solution. Treat a small amount of the compound with nearly 5 ml of the prescribed alkali solution and note down the change in the cold state. Observation. Inference. Mixture sets to a white solid. Esters of dibasic acids. Highly colorous solution. Nitrophenols, nitro acids, salicylaldehyde. Color becomes deep on standing. Polyhydric phenols, some aminophenols. Yellow to brown resin. Aliphatic aldehyde. Now heat the solution and note the change. Observation. Inference. Compound dissolves. Some esters or acid anhydrides. Ammonia is evolved. Amides, urea, thiourea, and sulfonamide. Yellow or brown solution. Sugars, except sucrose, polynitro compounds, halogenophenols, halogenonitrohydrocarbons. Chloroform-like odor. Chloral. 6. Action of hot concentrated sulfuric acid. Treat a small amount of the given compound with concentrated sulfuric acid, note the change and then warm it. Observation. Inference. Evolution of carbon dioxide without charring. Urea. Evolution of carbon dioxide and CO, and mixture becomes yellow without charring. Aliphatic hydroxy acids. Evolution of CO and, or carbon dioxide and SO2 with immediate blackening. Carbohydrates, aliphatic hydroxy acids. Blackening but no effervescences. Polyhydric phenols. Pungent vapors without charring or blackening. Carboxylic acids, simple. 7. Reaction with ferric chloride. This reagent is frequently used for identifying the presence of phenols and aliphatic alpha hydroxy acids. Take nearly 2 ml of the compound solution either in water or in alcohol and add to it 1 or 2 drops of neutral ferric chloride solution and note the charge as below. Observation. Inference. Red color but disappears by adding dilute HCl. Low fatty acids, malic acid or amino acid. Intense transitory bluish green color. O-phenylnediamine. Intense red-brown color or PPT. Ortho or methaphenylene diamine. Purple color. Salicylaldehyde, salicylic acid, salicylamide, acetyl salicylic acid, phenyl salicylate. Blue or red color. Phenols, resorcinol, cresols, aminophenols. Greenish color or PPT. Catechol, quinol, beta-nathol. Deep yellow color. Aliphatic alpha hydroxy acids. Pale brown PPT dissolves in dilute HCl. Decarboxylic acids soluble in water. Ferric chloride may also be used for identifying certain amines. In practice, the compound is dissolved in dilute hydrochloric acid and 2 drops of ferric chloride solution are added to the solution. Observation. Inference. Green or blue-green color. Diphenylamine, aniline, N-methylaniline. Violet color. P-anizidine. Red color. P-phenetidine. Red PPT. O-phenylnediamine. Blue PPT. Alpha-nathylamine, or toluidine. 8. Action of potassium permanganate. Potassium permanganate is a very important oxidizing agent in neutral, acidic as well as in alkaline medium. In neutral medium, dissolve the substance in water and then add to it 4 to 5 drops of neutral potassium permanganate solution with constant shaking. Violet color discharged in case of olefinic compounds. In acidic medium, perform above test using potassium permanganate solution acidified with dilute sulfuric acid and then warm the contents. Violet color discharged in case of olefinic compounds, aldehydes, ketones, oxalates and formats. In alkaline medium, perform the TET as in I, but using potassium permanganate solution made alkaline with a few drops of dilute sodium carbonate solution. Violet color discharged in case of aldehydes, phenolic acids, formates and cinnamides. In case color is discharged on warming alpha hydroxy acids, viz., citric, lactic, tartaric, etc., may be present.